Hey everyone, for the remainder of this chapter we're going to be talking about something called the fundamental theorem of calculus. And so based on this word, right, fundamental, this is a super important theorem for calculus. So we really want to make sure we've got this down. So today we're going to be focusing on part one of the theorem. So before we get into what that theorem actually says, we're going to do a little exercise here. Okay, so it says to calculate the following. So what we want to do is calculate the derivative with respect to x of the integral from pi over 4 to x of sine of t dt. So we want to actually calculate that. So I'm going to start by evaluating this integral, and then we'll go ahead and take its derivative. So let's evaluate this integral. Luckily, sine of t is definitely something that we know the antiderivative of. So the antiderivative of sine of t is going to be negative cosine of t, and we're going to be evaluating that from the value pi over 4 to x. Okay, and then when we're done with that, we'll take its derivative. So I'm just going to leave that there so we don't forget to do that. So now, if I take the derivative, I know that to evaluate this, I'm going to evaluate my upper limit. So I'm going to have negative cosine of x, and then minus a negative cosine of pi over 4. So let's simplify this. So I'm going to squeeze it in here. I have the derivative with respect to x. Now, negative cosine of x I can't do anything with. Let's see. Cosine of pi over 4 is root 2 over 2. So this is going to be a negative root 2 over 2. But now minus a negative is going to be plus root 2 over 2. So now in purple, I've evaluated that integral. I took its antiderivative, evaluated the top minus the lower limit of integration, and simplified. So there's our integral. So the next thing we want to do is differentiate with respect to x. So I'm going to show this in red, or I guess it looks orange on the screen. The derivative with respect to x of negative cosine x is going to be sine of x. And the derivative of root 2 over 2 with respect to x is just going to be 0. So I have sine of x plus 0, or sine of x. And so here's what I want us to notice. When we took the derivative of this integral, what we ended up with was just our integrand, and we substitute the x for that variable. And this is what actually is called the fundamental theorem of calculus part 1. Here's how it looks, and then we'll talk about what it means. So here's the idea. If a function f is continuous on the interval from a to b, then the function, we're going to call it capital F of x, equals the integral from a to x of f of t dt, has a derivative at every point x in a, b, and that derivative, the derivative of f with respect to x, which is the derivative with respect to x of the integral from a to x of f of t dt, is just f of x. So what we're really saying here is that the process of differentiation and integration are inverses. They undo each other. So when I do this, I just end up with my original function evaluated at upper limit of integration. Now there are a couple conditions here, and we'll talk about that in a minute. So first I'm going to make a note that the process of integration and differentiation are inverses. Okay, now the thing to notice here is this works only if we have a variable upper limit of integration So my upper limit of integration is a variable, or x, and I have a constant lower limit of integration. So just like in our example above, my pi over 4 was my constant lower limit. My upper limit was x, or a variable. So that what's told us, since these are inverse processes, the derivative of that integral was just sine of x. And so with just a few kind of caveats, it's going to be that simple. So we have three basic rules that we want to look at, and these are kind of the caveats that I was talking about. So the first one is just basic, right? Just plug in the x. So when taking the derivative of an integral whose upper bound has an x, that variable upper limit, we're just going to, I'm not sure what this was supposed to be, but we're going to say we're just supposed to substitute the x. So whenever I have just x here, and again, I double check my lower limit's a constant. So if I have just x up there, if I want to find dy dx, we know that dy dx is just the derivative with respect to x of our integral from 4 to x of sine of t squared dt. So since our upper limit is just an x, to get that derivative, all we do is we take our integrand and we replace or substitute our t with x. So sine of x squared. And we're done. So that's what fundamental theorem allows us to do. So when it's just x, it's simple. We just replace or substitute the dummy variable here. Oh, that's something I want to mention. We call this just a dummy variable. So that could be any letter that we want. It just has to be different from our limit of integration here. So when we have x as our upper limit, we just replace that variable with x to get our derivative. Now, something a little bit different happens when I have an upper bound that's a function of x. So instead of just x, you can see now here I have a function of x. So if our upper or lower bound is a function of x, then we need to multiply by the derivative of the function after we plug it in. So for example, if I want to find dy dx, I know that's the integral from 4 to 3x squared plus 7x of sine of t squared dt. Excuse me, this is the derivative of this integral. So now, fundamental theorem says, well, the first thing I'm going to do is replace t with this function. So I'm going to have sine of, now I'm going to be careful here, it's 3x squared plus 7x, quantity squared. So there's the first part. I'm going to get another color here. All I did for the first part, since I saw this was a function of x, was I replaced t with that function. But now we're going to multiply by the derivative of that function. So times 6x plus 7. And that would be my derivative. So first we replace t with our upper limit, and then we multiply by the derivative. Okay. Now, for this next example, I'm actually going to ignore this here because I look at it a little bit differently. Hopefully what you notice is this is reversed now. I have my constant is up top, and my function of x down here is in the lower limit. But we said to use this fundamental theorem, we wanted that constant down below. So all I'm going to do here is rewrite this using our property of integrals. I know if I want to change the order of integration here, I'm just going to take opposite, and then I can switch the order from 7 to 3x plus 2 of sine of t squared dt. So now I have my lower limit's a constant, so that's good. My upper limit is my function of x. So now it's just like the previous example. I'm going to substitute my upper limit for the variable and then multiply by the chain rule. or by the derivative, excuse me, because of chain rule. So dy dx, again, is opposite of the derivative with respect to x of 7 to 3x plus 2 sine of t squared dt. So again, fundamental theorem says take my upper limit and replace the variable. So sine of 3x plus 2 quantity squared, and then multiply by the derivative of my upper limit times 3. So I have negative 3 times the sine of 3x plus 2 quantity squared. All right, so let's go through some examples using the fundamental theorem. All right, so for number 1, I want to find the derivative with respect to x of this integral. The first thing I'm always going to check is my lower limit a constant, and in this case it is. And the nice thing, my upper limit is just x. So all we need to do is replace our variable in the integral with x. So that value is just going to be cosine of x. And we're done. Nice simple problem. Again, for number 2, I'm checking, is my lower limit a constant, which it is. Is my upper limit here is x. So again, since I don't have a function of x, I just have x, I replace the variable in my integral with x. So this is just going to be 1 over 1 plus x squared. So those are about as basic as these problems are going to come. So now let's look into some ones that require chain rule and some other techniques. All right, so for number 1, again, I'm always making sure, is my lower limit a constant? And in this case it is. I just happen to have my upper limit is a function of x. So I'm going to start off the same. I still substitute that for the variable in my integral. So let's see, find the derivatives. I'm taking dy dx. Here I want us to be very careful with our notation. The derivative of y with respect to x is the derivative with respect to x of our integral from 1 to x squared of cosine t dt. So now, by fundamental theorem, I replace my variable with my upper limit, so cosine of x squared. And now, since this is a function of x, I have to multiply by the derivative, or times 2x. So our derivative is 2x times the cosine of x squared. Okay, for number 2, my lower limit is a constant. So far, so good. My upper limit, I can see, is a function of x. So again, we're going to use that chain rule. So the derivative of y with respect to x is equal to the derivative with respect to x of the integral from 2 to e to the x of tangent t dt. So now I'm taking the derivative of my integral. That's going to allow me here to use fundamental theorem. So my e to the x goes in for t, so I have tangent of e to the x. And then I multiply by the derivative of e to the x, which is just e to the x. And then we're done. All right, moving right along. Number 3. Now here I see that things are a little different. Now my upper limit is my constant, and my lower limit is my variable. So again, I'm going to use my properties of integrals here, my order of integration, to flip these. So now I know this is equal to the opposite of the integral from 5 to x of, 3t sine of t dt. So in that first step, all I did was change the order. I haven't taken a derivative yet at all. I just changed the order of integration. So now my constant is my lower limit. So now I can go ahead and take the derivative, dy dx. It's the derivative with respect to x of our integral. I have an opposite here. I don't want to forget that. From 5 to x of 3t sine of t dt. So I have negative. Again, this is not a function of x. I don't have to worry about chain rule, so I'm just going to replace that everywhere I see a t. So it's going to be negative 3x sine of x. And that's my derivative. Okay, let's see. Next one. Again, I have a problem with my order here because my constant is up top and I have a function of x on the bottom. So I know I'm going to be using chain rule, but the first thing I want to do is change that order of integration. So I'm going to make it the opposite of 6 to 3 tangent of x of secant t dt. So now I'm going to differentiate. Again, please be careful with this notation in your notes so you get in the habit of having this nice notation. I've got my negative, and I'm integrating from 6 to 3 tangent of x secant t dt. So now, let's see, I'm going to replace t with my 3 tangent of x. So I have secant of 3 tangent of x. And then I multiply by the derivative of 3 tangent x, which is 3 secant squared of x. I forgot my negative here. So negative 3 secant squared of x times secant of 3 tangent of x. And that's done. All right, we'll just do one more here since we're getting close to our 20 minutes. Now, this one we have to be a little bit careful because what we notice here is that both our upper and lower limits are functions of x. So changing that order of integration isn't going to help us anymore because we're still going to have functions of x. So now what we're going to do is we're actually going to evaluate the upper, and then we're going to subtract the derivative of our lower term. So here's what's going to happen. This is going to look like this. We're going to rewrite this, and we're going to make it the integral from 0 to x squared of 1 over 2 plus e to the t dt. And we're going to subtract the integral now from 0 to 2x of 1 plus 2, or 1 over 2 plus e to the t dt. So I just split up this integral so that essentially what I could do is have two integrals now whose lower bound is a constant. So now if I'm going to differentiate it, I'm going to take the derivative of each one. Derivative with respect to x of 0 to x squared, 1 over 2 plus e to the t dt, minus the derivative from 0 to 2x of 1 over 2 plus e to the t dt. So now I'm going to differentiate each one of those. Again, I have a function of x. I'm going to have 1 over 2 plus e to the x squared times the derivative of that, which is times 2x. And now minus, let's see, I'll have 1 over 2 plus e to the 2x times 2. So for a little simplification, we have 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And that would be our derivative. So we're just evaluating really the top, taking the derivative at the top limit and subtracting the derivative at the lower limit. Okay, so we'll leave this here for today and we'll practice when we're in class next.